Hi, my name is Stuart Williams and I work for Magenic. And today's journey into Azure is about Azure Cosmos DB, which is the rebranded DocumentDB database, but it's also rebuilt from the ground up. Cosmos DB now subsumes DocumentDB and will soon subsume Azure Table Storage. It's a NoSQL database. In its Mongo and DocumentDB or SQL incalcations, it works best with JSON documents. But the same platform that was used to support the DocumentDB, SQL library, and Mongo DB interfaces also provides support for Azure Table Storage and for the Gremlin Graph API. And of course, like all Azure things, you can interact with it via the REST interface. Important note that your choice of DocumentDB, MongoDB, Gremlin, or Azure Table Storage modes is super important. Once you make a choice, that's the choice that you have. And if you have scenarios where you might need a mix of those things, you'll need to make separate Cosmos DB instances to subsume those use cases. Making a separate instance for each of your use cases, Mongo versus Gremlin versus Table versus SQL mode, is no big deal because like most Azure Platform as a Service things, it's a pay for what you use type of billing, and so there's no harm in having multiple instances, each configured for the appropriate API you need. In the use case where you have one set of data and you need to get at it through multiple APIs, you should probably consider picking the API choice that serves most of your business needs and scenarios, and then supporting other use cases via building an API or facade or web API to go over the top of it. So why is Cosmos a big deal? Cosmos DB is built on top of the service fabric, and if you watched our first episode about the triplets, speak about that. What this enables is highly scalable, resilient instances that will span regions, data centers, and even be global. It allows Microsoft to offer distinct and predictable consistency levels. And we'll talk about the consistency levels in a bit. A minimum of 4 nines of high availability right out of the box. You can actually get more availability if you're willing to spend a little more. SLAs are important because they're backed by a monetary guarantee by Microsoft. So what it allows from an architecture point of view and from an implementer's point of view is the sure and certain knowledge that certain query operations will be predictable in terms of their cost. And that allows you to figure out systems that will have very high scalability. Cosmos DB, like most NoSQL databases, does optimization and indexing for you. Practical hands-on work that we've done in almost every case indicates that letting Cosmos DB decide your indexing and other optimization strategies for you as it observes the actual use of the system is usually the way to go. We haven't found, in fact, a single scenario where we overrode the default settings where it figures things out for you. It's very cost effective and predictable in the sense that just like in Azure SQL, where there's a unit of consumption that's predictable, resource units, which are the unit of consumption for Cosmos DB, can be scaled up and down. You can even set them to auto scale so that if you have scenarios where you have bursty periods of use and idle periods of use, you can actually scale up and down the resource units that you configure your database for. So Microsoft has gone out of its way to address a number of common complaints about NoSQL data. So let's talk about the 4 modalities that Cosmos DB runs in. The first is a traditional DocumentDB mode. And it's used for JSON documents and attachments. DocumentDB has quite a number of libraries that are supported for accessing it. One of the things that we found when customers were migrated from DocumentDB to Cosmos DB, nothing broke. We didn't have a single instance where an app that depended on DocumentDB stopped working. DocumentDB is focused around using SQL syntax. In .NET, this is actually reflected using the typical builder pattern, in other words, using link expressions, which then are transformed into the appropriate SQL syntax, which of course is then applied via the underlying REST of API. If your Cosmos DB is in DocumentDB mode and you have to import a lot of data, please do use the import data tool. Please note that you should not use this tool if your Cosmos DB is in one of the other modes. There are plenty of good demos for DocumentDB on the interweb, and since it's been around for a while, we're not going to demo that. We'll show you some of the other modalities though, because those are interesting. Mongo DB mode. So Mongo is an incredibly popular NoSQL database, and there was a period of time in which there were a whole bunch of different competitors to Mongo, and Mongo has emerged as a standard as the clear winner for a bunch of reasons, not the least of which is that Mongo database servers ran on a whole bunch of different platforms. There was an enormous amount of community contributions. The actual wire protocol for Mongo is an open standard. There's plenty of third-party tools, and there are plenty of drivers for lots of different programming languages. My favorite tooling, parenthetically, is the Studio 3T tools, because it was one of the few tool sets that properly supported SSL. Likewise, we were successful in both Node and .NET Core, and we'll show you those demos in a minute. By the way, you can find the full source of those demos up on our GitHub site. Here's the Azure portal showing my Cosmos DB in its Mongo mode. I tend to name my databases eponymously for the driver. Here we have the Data Explorer view up, and I've done a query on some data I generated and imported. And you can read all about that by looking at the data generation tool, which generates NoSQL data like this chunk of JSON. So you can see here, I've executed a query against my data where I'm looking for anyone with a last name that starts with MC. So we get back McCandless and McQuisition and so on and so forth. This replicates the behavior of the Mongo experience pretty well. And in fact, there's even a Mongo shell. And like other Mongo instances, you can make a stored procedure, a user-defined function, a trigger, and so on. So let's look at some code that queries this data up in my repository. One happy note is, although I won't show it to you, this settings connection string tab is where you would get all of the important information to populate your connection string. It's also important that you know what the name of your database is and the name of your collection. Here's our little project in Visual Studio Code. And just to keep us honest and to prove the point that Cosmos DB running in Mongo mode is compatible, you'll notice that in the dependencies section, the only thing that we needed to npm into our little Node.js project was the default Mongo DB driver. Now, you could have used a fancier driver like Mongoose and so on, but just to prove the point, this is the Mongo DB driver for Node.js from the Mongo organization. Okay, let's look at our code implementation. Here we have a little block of code that goes and populates our settings, connection string, database, and collection. And we have a little chunk of code that reads that in from a file on disk called settings.json so that we have those things available. And then we invoke our doMongo function when we're done with that. And our doMongo function, we're going to do some very simple code that is going to create an instance of a Mongo database connection client object by using the connection string. And then we're going to set the desired database in. And then we're going to execute a little query using that database object, now pointing at the correct database, to find some records. And we're going to close the database connection, which you should always do. Make sure that whatever route through your code that you do, that you close the client. Our query is basically the same as we could execute through the Mongo console. So here we fire up our DB collection object. We execute our query. We turn it to an array. By the way, the alternative to this is to get a cursor object and iterate through the cursor. If you have a lot of data, using a cursor and fetching the data from the database in pages, so to speak, is probably better. But I only have 50 records in my sample database. And of those, only a very few are going to match MCA. And so in this case, I just to-arrayed the find results, and then I console logged the output. So let's go ahead and run this and take a look at the output. Since we have Node installed, Visual Studio Code knows how to invoke Node and execute the debugger. And you can see that our output window shows that we're connected to the demo data2 database, and we got back an array of results that we to-arrayed, and you can see that we have folks who start with MCA as the output result. Here's another Cosmos DB demo. This time we're going to use .NET Core. We could have used .NET CLR too, but we're using .NET Core just to show that you can. Same drill as before. Different mechanism. We're going to go grab settings.json off the hard drive, and it's going to have in it the connection string, the database name, and the collection name, so we know how to switch to. And I'll let you look through this code on your own. Another important feature is that we have a models folder. And in the models folder, we have, for example, the root object, which is our person object. And here, we had to do a little bit of work in C# to set it up so that the Mongo driver for .NET, which again, we're using just a straight out-of-the-box Mongo driver. And again, just to prove that to you, here's the .NET Core project, and here's the Mongo DB driver. So we added some decoration via some using statements, BSON, serialization attributes, and ID generators, and so on, to our person class in .NET, which is just a POCO object, and it contains a collection of addresses and a collection of settings. And again, you can look at the generated data from the data generator. But we had to do some things. The first thing we had to do was to ignore any extra elements. We've got some debugging elements and other things in our models. Those are great. We just have to tell it to don't panic if it sees extra elements. The other thing we have to do in .NET is we have a string property called ID, and we had to go to the trouble of telling it that A, this was the ID of the documents that we're storing in our Mongo database, and B, that the thing we're storing is a string. Under the covers, it was actually generated as a GUID. Didn't have a lot of luck with that, and don't really need it to be a GUID for the purposes of reading and writing data. So for this exercise, it's being treated as a string, and we're using the attribute to tell it that the ID should just be treated as a string. That's what that does. After that, we just map the element names to the property names. Now, in my case, the case and names for each of the elements are all the same, but it never hurts to go through and explicitly put the BSON element names on all of the elements that you're serializing. We decided the thing to do was to follow repository pattern. We're big fans of repository pattern at Magenic. Here's our Mongo repository class that we new up and pass in the settings that we got off disk. Those settings are injected. We can get them from anywhere. In this case, we're getting them off the disk. Notice that if there are required elements for your repository classes, it's a good idea to make the default constructor a private so that they have to invoke your constructor with arguments, the required arguments. The other thing we could have done, of course, is to provide a factory method, and that's okay too. We have a little validate settings method that basically just makes sure that all three of the settings elements aren't empty. And the main work is done by spinning up a new client instance of the Mongo client and feeding it our connection string. We have a database object which presumes that the client exists and calls get database on the right database. And now our database property of our client is connecting to the database that we desire. And lastly, we need a collection. In this case, the people collection, and the people collection is an iMongo collection of our person object. Here we're making a strongly typed Mongo collection so that we can use LINQ and enjoy the other benefits of having a strongly typed collection as opposed to default behavior, which is just a generic BSON document. You can manipulate those too, but we wanted to prove the point that you could use a strongly typed object in C#. We spin up our database, which we chain from our client object, and we say, okay, it's a person type. And of course, we point to the collection we want from our settings. And now we have a strong typed people collection that we can use to do queries on. In contrast, I want to show you what it looks like if you just want to get basic BSON back. In other words, the JSON objects that are in their binary or compressed form. Here's a method that uses our client object and our database object, but doesn't use our strongly typed collection object. And instead, we're calling database get collection. We're specifying, in this case, that we want a BSON document back. And we call collection find. And in this case, we're just going to get back all of the documents in our database. And we're going to consume those as a list of BSON documents. As opposed to our strongly typed methods, where we're using the strongly typed object, and in this case, we're using the Mongo DB drivers builders object to build a filter regular expression. And in this case, we're using our old friend name last and names that start with MC. But you can see that the syntax is slightly different. And using the builders on strong types, we can build all sorts of filter expressions using LINQ, including complex expressions with ands, ors, and so on. And for those of you who are comfortable using, for example, Entity Framework, you'll find that using the strongly typed LINQ syntax is very comfortable. And in this case, here is the wrapper function find, which takes any strong filter definition of type person and executes toList on it. Again, if I had a large number of records, instead of using toList, I probably would want to have a cursor and work with a cursor. But in this case, it's not necessary because I have very few objects and I wanted to keep my demo as simple as I could. And of course, here's the eponymous getById method. Notice that we're invoking people find and we can use a projection expression or a functoid. In this case, x underbar ID equals the passed in ID, and we're calling our old friend first to default, and then we're returning that model. So this is how you get back a singleton. Okay, we fired up our copy of our Mongo repository, feeding the settings. We're going to try to call each of the methods in this demo and get the results. So we're going to start by doing just the generic BSON. So we went after our collection, and instead of using the strongly typed POCO people, we're going to use the soft type BSON document, which is like dynamic in other parts of .NET. For those of you who have worked with generic JSON documents using the Newtonsoft library, you'll find that working with BSON documents is extremely similar. We get our list of BSON documents, we enumerate to our list, and in this case, for debugging purposes, we're calling the toJSON overload on our BSON object, and dumping the results out as JSON. So we'll see that when we run it. Here's some examples using our strong types. Here's our old friend, the regular expression starts with MC on the name last, and we get a list out of that, and then we call JSON serialize on that object and dump it out. What is list2 that we get back? Well, in this case, it's list of T on the person object. So it's just a strongly typed POCO object, and it can be serialized by Newtonsoft JSON converter just fine. Here's the same thing using a filter expression. And in this case, we're picking out a specific person, although it could be a whole collection of people if we had more than one person named Sincan. And we're using our builders to build an expression, a generic filter, and we're passing that filter to our find method. General reminder that find regular expression built a filter for us and then invoked the find method. So under the covers, it's running the same code. And for the demonstration, the next demonstration, we're remembering the resulting ID that came out of our list. And again, we just dump the resulting list out as JSON. We can call getById and get a singleton person object back and dump that to the output as well. Okay, here's our outputs. The first block of output is the BSON version where we went and got all the records, and in this case we enumerated through them, turned them each to JSON, and then dumped them out to the window. In our second case, we did a simple find using the Fluent or Link API to find the person who started with Sincan. And in the last case, we did a find where we had a specific ID, and of course we get back the same record again, and we dump that as JSON. This is a nice proof that using sort of the generic Mongo database driver for .NET, in this case for .NET Core, we're able to do all sorts of Mongo things. The next mode is Azure Table Storage mode. Azure Table Storage itself will be subsumed into Cosmos DB in the near future. New storage APIs on top of the DocumentDB NuGet package. The most important one is the in preview still storage premium table API, and we'll show you how that works in the demo. The one thing we noticed when doing a bunch of performance testing against the same amount of data in the exact same structure in Cosmos DB versus traditional Azure table storage is that the performance is startlingly better when your tables are in Cosmos DB. By way of a demo, we actually made a little utility that will generate a person table with a significant amount of fields, and that's going to serve as our demo as well. But you're welcome to go out to our GitHub site and give it a spin. To demonstrate Cosmos DB in its table mode, here's a little utility we wrote that will generate people for a people table, but it nicely demonstrates how we can interact with Azure Cosmos DB using the familiar table storage API. And we're going to start with our person entity, which is a table entity. Notice our using Windows Azure Storage Table, and we make a table entity. We have a special constructor. In this case, we decided to make the partition key the last name and the row key the first name. This is by no means a best practice. When we do that, it's important that we do a JSON ignore on the name first and name last properties so that we don't get bizarro problems when we serialize this. But other than that, this is a straight up POCO object, and you can see that there are just the regular fields. One unhappy thing that took a while to figure out with table storage is that you do need to make sure that you specify a converter for some of the .NET types, particularly .NET date time. Notice we didn't have to attribute every single property. The string prop, for example, are perfectly happy. So here's our main program, and is our want For console applications, we go through and we get our connection string properties, and that's not particularly interesting. What is interesting is that the code that we wrote that writes people entities to the storage is exactly the same code that we would have written to write to traditional Azure table storage. And we didn't have to do anything particularly exciting to make that happen. And so here's our little loop. We create a storage account using our connection string, make a table client. We say that the table client's payload is JSON without metadata. We create a table object by specifying the table name. In this case, it's our people table, and create the table if it doesn't exist. And then we just spin through and we create n number of records specified by our command line by calling our little helper person make. You can dig into that. But you can see that fundamentally we're creating a table operation object, in this case insert, and passing in the POCO class that we generated, which is a table entity type, and we call the execute method, and that result is that it inserts data into our table. Lastly, and the mode that's probably going to be the most novel for Microsoft and especially .NET developers is Gremlin. Gremlin is based on the idea that you want to have data structures that are expressed as a set of nodes and edges that have relationships. So we can say that Bob has a number of properties. He's a C# developer. He's blonde. He's 6'2", and he knows Tim, and Tim is brunette, and he speaks Java, and so on. The most important property is the verb of connection between the two nodes. So we can say that Bob is Tim's boss, or that Susan has friended John, or that John is in the Doctor Who fan club, and being in the Doctor Who fan club, he's related to Alice and Terry and so on. So particularly for social networks and the analysis of social networks and kind of walking social network graphs, Gremlin is a great way to do that. It's just a lot less than obvious. And you can learn more about Gremlin by looking at some of the Tinkerpop materials, which is where the most recent version of the Gremlin standard is. And Azure supports the Tinkerpop 3 standard mostly. And it does that through yet another preview API, Microsoft at Azure.graphs. And again, it supplements the Microsoft.Azure.DocumentDB NuGet pack. So we took the Microsoft demo and cloned it and made it a little more accessible, and you can find that out on our GitHub site to do that demo, in this case as a .NET CLR project in Visual Studio. Okay, here's our Gremlin demo that we mostly copied from the Microsoft demo. Couple of things. Notice the usings at the top include the Azure Documents namespace and a new namespace currently in preview called .graphs, which has the methods in it to manipulate graph objects. So let's get right to it. Again, we're going to parse the normal command line arguments looking for connection strings and the usual dross, and instead we're going to focus on the core of the demo code, which is do graph stuff, which is the demonstration of the Graph API. So the first thing we need to do is create a document client that's going to be in scope. This is far less than obvious about how this works. In other words, we need a URI to the storage endpoint, and we need an access key, which is the usual Microsoft access key. And then in sort of a database-y way, we specify the database name and the collection, in this case, people. So it's a sort of an odd hybrid of those two kinds of interactions. And that makes some aspects of using the API a bit perplexing. We start by firing up a document client. And again, we want to make sure if we create one of these that it gets destroyed. So we're doing it in the scope of a using. We create a database object. We had trouble when we made it asynchronous. So in this case, we're doing a bad thing and we're doing it synchronously by invoking the .result method to get a database connection object, which of course we're feeding the database name to. Same thing with the graph object, which you can think of as the collection, and we're using the collection name, in fact, to populate the graph object. So at this point, we have a working graph collection, which represents the graph and all its vertices. So we're going to use that graph object to do some work. Okay, here's Microsoft's little example that is essentially a collection of Gremlin commands and the narrative that sort of goes with them. Gremlin's syntax is far less than obvious. You can go look out on the Gremlin syntax tutorial. Again, Gremlin and graph APIs in general are not for the faint at heart. And you can see that we have a variety of Gremlin commands in which we create people and their relationships so that we have a graph. And we're going to show you what that graph looks like up in the Azure site. And of course, for convenience, we have a big list of these, but you could do them one at a time. Each one of these lines in the dictionary represents a Gremlin query. In other words, an atomic unit of work. And we're going to execute them one at a time. And then we're going to, as we execute that, we're going to get some results back. And we're going to spin through the results. And we're going to spit out what it says. So that's already a lot less than obvious. And we'll run this and show you the output. And you can see that the program outputs each of the commands as it executes, and then all the results of those commands. Okay, here's the Azure portal. We've opened up our Cosmos DB instance that we've configured for Gremlin Graph. We've clicked on our Graph DB3 database container. Inside of that, we have our people graph, which is a collection effectively, and we've clicked on the graph node, and we get an explorer that lets us take a look at the relationships between the nodes in our graph. So Thomas is kind of out there on his own. Here's Robin, and Ben knows Robin. And so you can see in the property pane that it describes the relationship between Ben and Robin. And so the converse should also be true, that Ben knows Robin and Robin knows Ben. This information about the nodes and their connections is actually stored as JSON. So here's the JSON version of that same graph showing Mary and Ben and Robin and Thomas and the relationships between them. A quick word about consistency levels, which is an important part of the fundamental idea behind Cosmos DB. First, we have to understand what consistency means. When writes happen, what's the subsequent read behavior? A lot of NoSQL databases have fewer consistency levels than that offered by Cosmos DB, or no well-defined levels at all. Cosmos DB offers a spectrum of consistency levels. At one extreme, reads and writes are linearized across all connections. At the other extreme, eventual, reads can happen out of order to writes across different clients. The default of session consistency means that for a single connection, the reads and writes will happen in logical order. Session consistency mirrors the behavior of SQL Server. If I'm a user connected to a SQL Server instance and I do a bunch of reads and writes, the effect of the writes are reflected back to me when I do the subsequent reads and vice versa. In other words, I don't get dirty reads. Different consistency levels offer architects and designers a lot of choices in order to balance the latency between the time something is written and the time something is read and its consistency. In some scenarios, session consistency is probably the right thing. In other more rare cases, strong consistency is needed. In some cases where there are a lot of writes and the reads are going to happen much later in time, eventual consistency is not only good enough, but offers other benefits. You can read more about this in the Microsoft documentation. I hope this has been a helpful overview. Thank you for watching.